Hello from OzU Rover team at OzU University in Istanbul, Turkey. We are a team of 20 passionate students. Today we are proud to present our latest generation rover, RS4.
As the mechanical sub-team, this year our primary goal was to ensure rover's structural durability and operational reliability. For our new locomotion system, we are building a sturdy yet lightweight framework combining carbon fiber tubes with custom aluminum CNC machined links. While retaining our rocker buggy suspension, we optimize the track width to improve lateral stability during skid steering maneuvers. We are integrating new BLDC motors with high torque outputs to meet the necessary traction. We prefer to use our previous wheels, which were manufactured using 3D printed ABS rims with TPU phase skin tires. The main chassis geometry is preserved from last year and features a custom topology optimized design, manufactured from 2mm galvanized steel. For the new 5 degrees of freedom robotic arm, we again utilized carbon fiber and aluminum to maintain a rigid, lightweight profile. To handle higher payloads and dynamic loads, we reinforced the arm-to-chassis base interface, significantly improving load transfer during manipulation tasks. For actuation, we integrated our existing BLDC motors with high-ratio anti-backlash worm gear reducers, prioritizing torque capability and positional repeatability. Dual lead screws drive the linear motion of our end effector, featuring interchangeable TPU jaws and an integrated slip ring for continuous 360-degree rotation.
This year, as the electronics sub-team, while building on a solid foundation from last year, we focused on improving system reliability, communication, and integration. From last year, we continued using NVIDIA Jetson Orin as our main compute unit, and we kept our robotic arm architecture where the ARC'26 actuators are controlled over CAN protocol. This setup is already proven in terms of stability and fault handling, so we kept it as a reliable baseline. On top of this baseline, we introduced several key upgrades this season. For locomotion, we integrated our new drive motors using Ethercat. This is a major step forward for drivetrain, enabling high bandwidth, real-time communication, and better synchronization across the system. As a result, we get smoother motion behavior, more consistent response, and a stronger diagnostic capability during operation. We are upgrading our communication link with new 5 GHz antenna solution to increase bandwidth and reduce interference, especially important for telemetry and responsive remote operation in mission tasks. For the science system, we made minor upgrades to the science board and its integration. These improvements boosted the stability and helped the science subsystem run more smoothly and consistently during the operation. In terms of safety, we kept our emergency stop strategy from last year as a core strategy layer to quickly place the rover into a safe state when needed. We also support power safety through battery management. We use BMS to monitor key parameters like voltage, current, and temperature to protect the system during operation.
For command and control, a web-based graphical user interface featuring low-latency WebSockets is utilized. To mitigate field overloading across all radio bands, we developed a context-aware bandwidth management system that dynamically prioritizes high-resolution video streams based on the rover's kinematic state, like automatically focusing on the rear camera while reversing, optimizing our radio link without sacrificing situational awareness. Driven by a Z2 stereo camera, our autonomous navigation stack processes 3D point clouds into a 2D occupancy grid for real-time mapping. To navigate, a custom path planning algorithm evaluates sector averages to identify traversable terrain, ensuring continuous obstacle avoidance. We fuse GPS telemetry with visual tracking to accurately reach waypoints. If a target is not immediately visible, the rover executes a systematic search pattern to autonomously locate and log AR tag. This reactive autonomy is extensively validated in simulation before field deployment.
Finally, to keep it safe, our software has an emergency stop. It stops the motor immediately so the user can take control right away.
This year as the science team, we focused on improving the reliability of our sampling system. Similar to last year, our sampling mechanism uses a drill driven by a DC motor, while a second DC motor controls the vertical motion of the system. With this setup, we can collect samples from depth of up to 30 centimeters. To enhance sample integrity, we upgrade our sample storage unit. We introduced a new container with improved sealing, reducing the risk of leakage and contamination compared to previous year.
For analysis, we used the Bradford assay with QMASI Brilliant Blue, which shifts its absorbance peak from around 470 nanometers to 595 nanometers. When it binds to proteins using a CCD-based spectrophotometer, we capture the full absorption spectrum and visualize the absorbance data as a graph, enabling more precise interpretation. In addition, our module includes a sensor suite to monitor environmental conditions. As in previous years, we measure air quality including ozone, carbon dioxide, and carbon monoxide. We also measure pH, humidity, soil moisture, temperature, and light intensity, which can help us assess habitability indicators and infer the potential presence of water-related environments.